Hi, everybody. It's Professor Mitchell, continuing with Chapter 10. In this video, we'll look at Section 10.2 on annuities. An annuity is a sequence of equal payments made at regular intervals of time. The payments are called rent. The amount in an increasing annuity gets larger with each payment. So an example of that would be like a retirement fund. And the final value is called the future value of the annuity. The amount in a decreasing annuity gets smaller with each payment, and the amount at the beginning is called the present value of the annuity. So an example of this would be like a mortgage. For example, parents decide to deposit $100 at the end of each month into a savings account for the college education of their child. After 216 payments, the account will contain $38,735.32. Having just won the state lottery, you decide not to work for the next 5 years. You want to deposit enough money into the bank so that you can withdraw $5,000 at the end of each month for 60 months. If the bank pays 2.1% interest compounded monthly, you must deposit $284,551.01. The first example is of an increasing annuity with a rent of $100 and a future value of $38,735.32. The future value of an increasing annuity of n equal payments is the value of the annuity after the nth payment. The second example is of a decreasing annuity with a rent of $5,000 and a present value of $284,551.01. The present value of a decreasing annuity is the amount of money necessary to finance the sequence of annuity payments. That is, the present value of the annuity is the amount you would need to deposit in order to provide the desired sequence of annuity payments and leave a balance of zero at the end of the term. All right, so here comes the formula that we'll use to calculate this. Suppose that an increasing annuity consists of n payments of R dollars each, deposited at the ends of consecutive interest periods into an account with interest compounded at a rate I per period. Then the future value F of the annuity is given by this formula. F equals 1 plus I to the n minus 1 divided by I times R. In this example, we'll calculate the future value of an increasing annuity of $100 per month for 2 years at 6% interest compounded monthly. Capital R is 100. I is 0.06 divided by 12. Remember, I is the interest rate per period. So as a decimal, that comes out to 0.005. And n, the total number of payments, is 2 times 12, which is 24. Therefore, F is equal to 1.005 to the power 24 minus 1. Divide that by 0.005 and multiply by 100 for a future value of $2,543.19. So what I would like to do here is switch over to the calculator and show you how I like to do this on the calculator, because this formula is a little bit more complex. All right, so I think the simplest way to enter this formula is kind of in pieces. So I'm going to put 1.005 to the power 24 and then subtract 1. I'm going to ask for that answer, And then I'm going to divide that answer by 0.005, and then finally multiply by 100. All right, so actually, I would round that answer to $2,543.20. I think they had 19 cents, if I remember correctly. What you have to remember is that fraction at the beginning of the formula, the numerator is 1.005 to the power 24 minus 1. And if you're determined to put all of that in at once, it has to go in parentheses. So another way to do it would be like this. Okay, and then you can do times 100. So you get the same answer. I personally think the first way saves you a couple of keystrokes, but just find a way that works for you and stick with that way. That is my advice. All right, so now I'm going to switch back to presentation. All right, so for the next example, Ms. Adams would like to buy a $300,000 airplane when she retires in 8 years. How much should she deposit at the end of each half year into an account paying 4% interest compounded semi-annually so that she will have enough money to purchase the airplane? All right, so in this example, F, the future value, is given 300,000. I, the interest rate per period, is 0.04 divided by 2, which is 0.02. And the total number of payments is 8 times 2, which is 16. So using the same formula, this time the unknown is R. We're trying to find the unknown regular payment. So we get 300,000 equals 1.02 to the power 16 minus 1. Divide that by 0.02 and then multiply by R. So we're going to calculate this quotient, which comes out to about 18.63928, blah, blah, blah. So now in order to solve for R, we need to divide both sides by 18.63928, blah, blah, blah. And when you do that, you get R is $16,095.04. So in order for Ms. Adams to be able to buy an airplane in 8 years, she's going to have to deposit a little over $16,000 into her account every 6 months for 8 years. All right, so the present value P and the rent R of a decreasing annuity of N payments with interest compounded at a rate I interest per period are related by this formula. P equals 1 minus 1 plus I to the power negative N divided by I times R. So this is for a decreasing annuity. So notice the formula is a little bit different. The terms on top are switched. This exponent became a negative N. All right, so for a couple of examples, how much money must you deposit now at 6% interest compounded quarterly in order to be able to withdraw $3,000 at the end of each quarter year for 2 years? So this is kind of similar to the scenario earlier where the person won the lottery and wanted to be able to take out $5,000 a month. So in this problem, R is 3,000. I is 0.06 divided by 4, which is 0.015. And the total number of deposits will be 4 times 2, which is 8. All right, I think this might be another good one to switch over to the calculator for. All right, so this is the answer that we're hoping to get. Let me switch over to the calculator again. I just hope I remember. Hold on a second. Okay, I was a little worried I might forget the numbers. I can't see them when I've got the calculator up on my screen like this, but I think I've got it. It's 1 minus 1.015 to the power -8. And then we're going to divide that by 0.015 and multiply by 3,000. $22,457.78. Let's see. Okay, perfect. That's exactly the same answer they got. Okay, and then for this example, if you deposit $10,000 into a fund paying 6% interest compounded monthly, how much can you withdraw at the end of each month for 1 year? This might be a good one to pause the video, try it, and then come back and compare notes. Okay, so in this example, P is 10,000. I is 6 divided by 12%, which as a decimal is 0.005. And the number of withdrawals is 12 times 1, which is 12. All right, so we're given the value of P and we have to find R. All right, so that ends up looking like this. 10,000 equals 11.6189, blah, 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 times R. So divide both sides of the equation by 11.61893, blah, blah, blah. And we get that R comes out to $860.66. All right, so to summarize this section, an increasing or decreasing annuity is a sequence of equal deposits or withdrawals made at the ends of regular time intervals. F, the future value, compound amount, or balance, is the value in an annuity at some point in the future. R, the rent, is a periodic deposit into or withdrawal from an annuity. The future value of an increasing annuity is calculated with this formula, whereas the present value of a decreasing annuity is calculated with this formula. And this didn't come up in any of the examples, but successive balances of an increasing annuity can be calculated using B sub new equals 1 plus I times B sub previous plus R. And for a decreasing annuity, it's the same formula, only with a minus. But the formulas on the preceding slides are probably going to be more useful because all you can do with these, they don't get you right from the beginning straight to the end. This is okay, like if you're trying to find the balance after 1 month, after 2 months, after 3 months. But if you want the balance after 5 years, you would want to use the other formula or formulas, depending on whether it's increasing or decreasing. And that's going to do it for section 10.2. We'll see you next time.